drag force F acting on a sphere of radius r falling at constant speed v through air is given by this equation, where k is a constant. So we have a sphere falling, radius r, falling at speed v, and it has a drag force F, k, r, v. For a sphere of uniform density and mass m falling at a constant speed, the drag force heats the surrounding air at a constant rate, p. So p would equal, well, we can easily see this would be F times v. So it will be KRV squared. Don't need to write that down yet. Don't know how important that is. But this is the first thing I think of when seeing this. Another sphere of the same material, so same material, which means same density, but with mass 8m, so it's going to have 8 times the mass, which means it's probably going to have a larger radius. This falls through the air at a different constant speed. What is the rate at which the drag force on the heavier sphere heats the surrounding air? So we need to understand the mechanism by which this is happening. So if we have spheres falling at some constant speed and they have a drag force, that must mean the drag force is balancing the weight term, because it's falling, and then if there was a drag force on it, if there was a net force, it would be decelerating. But clearly it's traveling at a constant speed, which means that the forces on it must be balanced. So the only one we could assume here is gravity. So looking at these equations and seeing what we can do, we have that the mass of the object times g equals k r v. And then because we know the mass is proportional to density and radius cubed, so if we have density and then I'm just going to write here r cubed g, we can see that v is proportional to the radius squared. I ignored the 4 over 3 pi because it's not really relevant here, because I just wanted to determine a dependence between v and r. And why might that be useful? So why would we think to do this? Well, we know the power is F times v, so we just need to work out what the force would be and what the velocity would be. And so we need to know how the velocity depends on r, as well as the force, and how all these constants are related to each other. So for a sphere with mass 8m, if you notice 8 is 2 cubed, so because a sphere's mass depends on r cubed, the mass 8m must have a radius of 2r. So it has 2r for its radius, which means the velocity will be 4 times larger. So it will have a v of maybe 4. Well, it will be 4v compared to the original. So we can say P equals F of V. So P equals the drag force, K R V squared. And then looking at each term, the radius will double, and then V will actually multiply by 16. So this will be 2 times the 4V squared is 16. This is equal to 32. So we have 32p is our answer. That's a really large rate compared to the other one. So because this is 2 times larger, it has a larger terminal velocity, which depends on r squared. And then it also has a larger radius just due to its mass and having a constant density due to and it being made of the same material, so density is shared between them. And so we have 32p is the answer. So the main thing with these questions is to determine the mechanism at which it's heating. So it's P equals F of V gives us our power dissipated. And then we know P would equal KRV squared. So we just need to see how V would change and how R would change. V we can determine using balancing forces. And then R we can determine by just seeing how the mass has changed and knowing the density is constant. So you could think of it as working backwards and then working forwards. Or you could just see, if you were working out some equations, what things are we missing? What do we need to work out. Hopefully this makes sense, but if you have any questions, please let me know in